This is a lecture that completes our discussion of the quantum mechanical model of the atom. The last lecture took us through Niels Bohr model of the atom. And just as a quick reminder, Bohr discovered that electrons are quantized, which simply means they can only exist in certain energy levels. And so here is a typical Bohr model, and that's the model that shows rings around the nucleus. The rings represent energy levels. And Bohr's model, even though, even though it's not entirely accurate, is still used quite a bit because the fact is that electrons really are quantized. They can only exist in certain energy levels. And so by knowing what these energy levels are for an atom, we can find out what the energy gaps are between levels. So if you remember, if an electron jumps from a lower level to a higher level, it absorbs light. It has to get energy from someplace, right? Or absorbs energy. Doesn't have to be light. And then any electron doesn't stay in a higher energy level. It very quickly drops back down to the ground level, the lower level. And when it does so, it lets off that excess energy as light. And we can calculate the wavelength or energy of that light let off. So Bohr's model is still really useful. However, Bohr still, at his time, still believed that the electrons orbited the nucleus. That is absolutely not true. So that's very important you understand that. Electrons are very mysterious, if you haven't picked up that already, and we're not exactly sure how they move due to something called the Heisenberg uncertainty principle, which we won't go into right now. But they certainly, we know for a fact, they don't orbit the nucleus. The next big breakthrough in development of the quantum mechanical model of the atom came with Louis de Broglie. And he proposed, there was a lot of talk and work going on about the dual nature of light, that it could behave as a particle or as a wave. And so Louis de Broglie proposed that matter, specifically electrons, but any type of matter, which we think of as having particle behaviors as far as physics, the law of physics, could also have wave properties. And that opened up a whole new door that really was, that led directly to the quantum mechanical model. And so he said if matter is associated with wave-like properties, that means that every type of matter is also associated with some wavelength. And de Broglie's formula, which we're not going to do calculations with, but you should be familiar with it. Remember what H is? That's Planck's constant. So really what I want you to get out of this formula is that the wavelength associated with a particle of matter is inversely proportional to the mass of the particle times the velocity. Okay? So as the particle gets larger and larger, the wavelength gets smaller and smaller. And so the reason that's important is when de Broglie first suggested it, other scientists said, well, if matter is associated with wave, then why can't we detect waves with all sorts of objects? A human being, a car, whatever. And he used this formula to explain, saying, okay, if you have a large, quote, particle of matter, like a human being or a car, its wavelength is going to be so infinitesimally small because the mass is large that we're never going to be able to detect it, even with our sophisticated equipment. On the other hand, if you have really small particles of matter, like the electron, so that means mass is very, very, very small, and wavelength becomes large enough in order so that it can be observed, at least indirectly through experimentation. So ever since de Broglie made the suggestion that electrons might have wave-like behavior, and it turns out that Schrodinger built up on de Broglie's work and said, he was a mathematician, and said, okay, if electrons have wave-like behavior, I can write a mathematical equation describing the wave-like behavior. And these mathematical equations describing the wave should make sure that the wave fits perfectly around the nucleus of the atom. And so Schrodinger went ahead and did so, and he came up with extremely complex mathematical equations, which don't make any sense to me. You're welcome to look them up. But it turns out that when you solve those mathematical wave equations and plot them out, like we often do with equations, you get these regions of space, which we now call orbitals. An orbital now, according to the Schrodinger quantum mechanical model, is simply, again, a 3D region of space in which the electron is most likely to be found. And we're going to talk about the different shapes that were graphed from these Schrodinger equations. But the bottom line, just to kind of emphasize, Schrodinger's, the current quantum mechanical model, Schrodinger's, orbitals, again, are not a physical entity. They just define just an area of space where the probability of finding the electron is high. All right, so solving the different wave equations for the different orbitals around an atom, Schrodinger came up with spherical solutions for some of them, and we call those s orbitals. And dumbbell-shaped orbitals that we now call p orbitals. D orbitals, most of them are clover-shaped, except for this fifth funky one. And F orbitals, of course, the most complex, and I don't even know if there's a word to describe these. And what also came out of the wave equations that Schrodinger developed are what we call quantum numbers, and they're just integer solutions to the different wave equations for different atoms. Quantum numbers, in a real simplistic way, think of as the address for an electron, okay? So every electron in an atom can be precisely described in terms of its energy, general location, orientation in space, spin, all that with 4 quantum numbers. And every electron in an atom has unique 4 quantum numbers. So we're going to go over each of these individually. The first is n, lowercase n, which is the principal quantum number, and that it represents Bohr's energy levels around an atom. N must be integers, and n corresponds to the period on the periodic table, or the row, in case you don't remember, a period is a horizontal row on the periodic table. And so we begin to learn the symbolism. So if somebody says it's a 1s orbital, that means the principal quantum number for it is 1, and it also means that it's talking about an electron on the first row or first period of the periodic table. One of the things I want you to look at is in this Bohr model, what happens to the energy distance between orbitals as we go to higher and higher orbitals? Hopefully you notice that the distance between orbitals decreases as you go to higher and higher. So the difference in energy between, let's say, n equals 1 to n equals 2 is much greater than the energy difference between, for example, energy level 3 and energy level 4. So that's an important little tidbit to know also. All right, so you may remember the Rydberg equation, and we were using it to calculate the energy gap between 2 energy levels. It turns out that you can actually calculate the energy of a specific energy level also using this equation. And just by tradition, you can see this Rydberg equation sometimes has a minus sign, sometimes doesn't. And the reason being is that energy levels around an atom, just by nature, are given a negative value. And in the world of energy, negative is a favorable thing. It means it's lower in energy, it's more stable. So let's just say an electron around an atom is more stable than a free loose electron, and so it's given a negative. But in any case, the equation, when we were calculating the energy gap between two different levels, it was 1 over n squared, the final level, minus 1 over n squared, initial level. Okay, so just kind of prompt your memory there. All right, the second quantum number, the first one was n, primary energy level. The second one is a cursive L. It stands for angular momentum quantum number. But the bottom line is that tells us something about the shape of the orbital. So if we are talking about a spherical orbital, that's an s orbital, and it's assigned an L value of 0. So anytime you see L equals 0, that is an s orbital we're talking about. P orbitals have an L value of 1, D orbitals have an L value of 2, and then of course, I don't know why I left out F, F orbitals have a value of L equals 3. So the values that L can have, they always start at 0 because that's S, okay? And they go up in integers, S, P, D, etc. Now, the one thing that's important to realize is the maximum value that L can have is n minus 1. So, for example, if if n is 2, if the primary energy level of an electron you're talking about is 2, what are the values that L could have? Well, L always starts at 0, and then the maximum value it can have is n minus 1. So if n is 2, the maximum value L can have is 1. So in this case, the example with n equal 2, L could either equal 0, which is an s orbital, or 1, which is a p orbital. So just kind of summary in table form, the different values of L and the orbital shape that they're associated with. Here's the practice problem, and let's see if you can answer it. So I suggest putting this video on pause and seeing if you get the right answer. All right, hopefully you tried it out on your own. So if n equals 3, the values that L can have, remember it always starts at 0, and the maximum it can have is n minus 1, so 3 minus 1 is 2. So L equals 2 is the maximum value it can have. So the correct answer is C. Alrighty, the third quantum number is m sub L. That is called stands for the magnetic quantum number. That represents the orientation of an orbital in space relative to other orbitals. So think of the x, y, and z axes, and or if you were graphing something in a 3D fashion, it would show its directional orientation. So this gets a little funky, but to try to explain it, but it's easier for me to explain it in person. S orbitals are spherical and can only be oriented one way. So if I have a ball in my hand and it's all the same color and shape and everything, and I tell you to close your eyes, and then I spin the ball around while your eyes are closed, and you open your eyes, will you be able to tell that I spun it around, or is it going to look identical? It's going to look identical. So s orbitals have one orientation. On the other hand, p orbitals that look like a dumbbell, so if I was holding the dumbbell straight up and down, like along the y-axis, and told you to close your eyes, and then I rotated it open your eyes, it would look different. It'd be in a different orientation. So basically, p orbitals can be oriented along the x-axis, the y-axis, or the z-axis. And there are 3 different orientations for the p orbital. So that's what m sub l tells us. And the values it can have, it varies from negative, whatever the value of l is, to positive, whatever the value of l is, proceeding through integers, okay? And it always goes through 0. So if L is 1, which remember is a p orbital, what are the values m sub l? Well, it goes from minus L to L. And since L is 1, m sub l can be minus 1, then it always goes through 0, and then plus L, which is plus 1. All right, so p orbitals, as I just said, have 3 different orientations in space. And that represents one of the orientations. That's the second one, and that's the third one. All right, so here is another sample problem. And again, I recommend that you turn off the video, see how you can do it yourself. All righty, so if L equals 2, what are the values that m sub L can have? Now, on the last slide, if you remember, I said m sub L goes from minus L, always goes through 0, and then its maximum is plus L. So what are the values that m sub L can have if L equals 2? Minus 2, go integer by integer, minus 1, 0, plus 1, plus 2. So the correct answer is D. Alrighty, the 4th quantum number is m sub s. That's a really simple one. It describes the spin of the electron, and it can either be spinning clockwise or it can be spinning counterclockwise. Okay, so by convention, if it's clockwise spin, we say that it's spin up and we designate it with an upward pointing arrow. And if it's counterclockwise, we say that it's spin down and we use a downward pointing arrow. The numerical values that are assigned to m sub s, the spin quantum number, are plus 1 for spin up clockwise, or plus 1 half, or minus 1 half, spin down for counterclockwise. Here's a brief recap of the 4 quantum numbers to make sure you kind of got them all and their allowable values. Getting close to being done here. All right, so again, every single electron has a unique set of 4 quantum numbers. Every single electron in an atom has a different quantum number than every other electron in that same atom. Every orbital, you may not know this, but every orbital can hold, however, 2 electrons, okay? Can hold 2 electrons. So N, L, and M sub L together, those first three quantum numbers describe one specific orbital. The MS is used to describe the fact that there can be 2 electrons in each orbital. Okay. So if you look at the periodic table, and we'll go over this more in the next lecture, but of course you have the horizontal rows, which correspond to n equals 1, n equals 2, and it goes down to n equals 7. Okay. And so it turns out that those are primary energy levels or principal energy levels, but the L values, the S, P, D, F values, are actually in the periodic table too, which again we'll talk about specifically later. But it turns out that group 1 and 2 represent the S sublevel, and the groups to the far right represent the P sublevel, the transition metals, the D sublevel, And the extra elements down at the very bottom, some people call them the intertransition metals, those represent the F sublevel. So there's a certain ordering of energy levels, and that, again, if you think of Bohr's model where you have the nucleus and then the allowed energy levels around it, there are specific energy levels that are allowed for an electron, and within each energy level there are sublevels represented by the L value. So in the n equal 1, or the first period, okay, there is only S sublevels. In the n equal 2 period, there are S and P sublevels. So in the second period, we have 2s and 2p orbitals. In the third energy level, we have s, p, and d orbitals. So there can be 3s, 3p, and 3d orbitals. This is just looking at it again, because it's a very kind of abstract topic, so don't get frustrated if you feel lost. I promise you, if you work with it a bit, it'll make more sense. So again, looking at the various orbitals that are could be in an atom in order from lowest energy to highest energy. Of course, lowest energy is always n equal 1. Then if n equals 1, the L values, remember L always starts at 0 and the maximum is n minus 1. So if n equals 1, L can only have a value of 0, which is an s orbital. If you go back to the rules for m sub L, it varies from minus L to positive L. But if L is 0, that means that m sub L must also be 0. All right, then as we said on the last slide, if n equal 2, L can either equal 0 or 1. And of course, then the allowed values of m sub L are different. So just try to do some practice. I'd start working on one of the practice worksheets to get a feel for these different main energy levels and sublevels. So here's a typical type of question you might see about quantum numbers. What are the quantum numbers and the names for the orbitals, all of the orbitals, in the n equals 4 principal energy level? And how many n equals 4 orbitals exist? Now, this is probably an overwhelming question at this point for you, but if for some reason you really got this and you want to try it on your own, go ahead and put the video on pause and give it a shot. Okay, so I always start with n, and then I just work my way down to all the possible values of the 4 different quantum numbers. So if n equals 4, what are the values L can have? Well, L always starts at 0, which is an s orbital, right? Then it proceeds in integers up to n minus 1. So L can be 0, 1. It can also be 2, which is a d orbital. And it can go up to n minus 1, which in this case is 3. Okay, so the fourth energy level has sublevels S, P, D, and F. So what are the quantum numbers and names? I just gave you the numbers. What would be the names of the orbitals in the fourth energy level? All right, so 4s, 4p, 4d, and 4f would be the names of all of these orbitals we just figured out. The second part of the question is how many orbitals are in the n equal 4 energy level. This is a handy dandy little relationship, so I would make sure you jot it down. So the number of orbitals in any energy level equals whatever the energy level is squared. So if we're in n equal 4, there are 16 different orbitals. Alrighty, we have reached the last slide in this lecture, and these are just handy little tips that'll help you with some multiple type questions on quantum numbers. So the number of sublevels within a level is n. So let's look what I'm talking about. If n equals 1, that means there's only one sublevel. If n equals 2, there are 2 sublevels. Let's just do one more. If n equals 3, there are 3 sublevels. Let's just double check. What is the one sublevel if n equal 1? Well, it's s, right? What are the 2 sublevels if n equal 2? S, P. What are the sublevels if n equals 3? Then it can be S, P, or D. And of course, 4 is SPDF. The second one, the number of orbitals within a sublevel, okay, is 2 times whatever the value of L is plus 1. So let's start really simple. Let's say that n equals 1, first energy level, and let's say then L, of course, has to equal 0. And this tells us that the number of orbitals within a sublevel are 2L plus 1. So if L equals 0, 2 times 0 plus 1, okay, that equals 0. Okay, so that tells us that in the sublevel, L equals 0, there is only one orbital, which is S. So let's do one a little bit more complicated. Let's do n equal 2. Okay, if n equals 2, the value that L can have are 0 or 1. We just did 0, so let's do L equals 1. If L equals 1, let's see how many orbitals can be in that sublevel. So now it's 2 times 1 plus 1. So that tells us there are 3 orbitals when L equals 1. When L equals 1, we're talking about a p sublevel, and we know that p sublevels contain 3 orbitals. And finally, what I just went over in the last slide, the number of orbitals in an entire level is n squared. That is it for this lecture.